All right, welcome back to HTH 2021 CTF Solve video series. Wow, that's a lot. In this video, we're going to be taking a look at the fourth challenge, which is in the crypto series, which is on electronic codebook AES. So let's take a look here. All right. So this one is called Attacking Codebooks, and Attacking Codebooks ended up being the hardest challenge. Nobody solved this one. And you're going to be able to see why. This is a bit of a doozy to try to explain, but we'll see if I can do it decently. Didn't start off with a hint, but we ended up giving one, which was a great article on Zach Grace's blog that tells you information about how to attack ECB. And then what we're going to do now is I will go ahead and paste in the challenge server. So we're going to connect over Netcat to this particular IP and this port. And it's going to tell us Nexus Secure AES ECB encryption service. What's the plain text? So we'll give it an A, for example, and it spits back our ciphertext. If I give it 2 A's, it pads that out to another block size. If I give it 3 A's, there's no additional padding on this right now, just different padding. So we'll end up seeing how this works. So we got this small amount of data right here. We double the size to this one. And if I eventually just keep putting in more and more and more data, it's going to get being padded out more and more and more. And the reason for that is the way that Ecb pads stuff. Let me go ahead and stop for a second and show you the file that we gave to players was this one. So obviously the file that runs on the server ends up having the stuff populated, but we sanitize it when we give it to the user. So what we have here is we prompt the user for input. They will give us input. We'll strip off new lines and carriage returns, and then we take that value and put it into plain text. Plain text converts that string to bytes. Then we'll take that plain text value and then add the bytes version of the flag. And then it's going to make sure it's padded out to 16 bytes, which is our block size. So in this case, our key is going to be 16 bytes. Oops. Or 128 bits. Okay. From here, we don't know how long the flag is just yet, but we'll be able to tell that very soon. We go ahead and create an AES object, and we tell the key that's going to be used, the mode that's going to be used, and finally we say with that cipher object, we want to encrypt this padded data, and then we send it back in ciphertext. So that's exactly what we're seeing going on here. So let's talk a little bit about padding with AES ECB mode. So this is a block cipher, meaning we need very specific size blocks, right? So if the block size is 15 and I only give it one character, it needs to pad that out somehow to 15. It doesn't just choose random bytes. It doesn't use just null bytes. What it'll do is take the length, the amount of bytes that it needs, and it will go ahead and add that number of bytes in that value of byte. So watch this. If I have something like a capital A and I just put in 1, a capital A is 41 in hex. If I put in that 41A, what it's going to do is it's going to say I need 15 bytes to pad. So I'm going to put in a hex 15 times. If I put in 41 or 2 A's, 2 capital A's, which is 41, it's going to say, okay, I need to pad this out to 16. You've only given me 2. I need now 14. So I'm going to put in 14 bytes. So I'm going to put 14 E bytes in. And it's going to continue to do this all the way down to here. Now what happens is once we get to our input being the exact block size, it doesn't just say, good, you're at 16 bytes. Our block size is 16 bytes. We don't need to add padding. It always adds padding. So what it'll do is it'll add an entire block of padding. So it'll add an entire 16 bytes of 16 byte block size, right? So it's going to make sure that there is always padding. So once we hit the actual size that then causes a whole new block to appear, then we know we found the boundary of what our actual flag size is. So watch here. So if I go up here and I enter in 1A, we haven't hit that yet. If I go up here and I enter 2 A's, we now all of a sudden have our original block plus a whole other block on the back side. So that means is if we take 16 bytes or 16 blocks minus our input, which is 2 A's, it's going to be 14. So our actual input, our flag that is added to this thing, right? Remember, we knew there was a 16 block because it was in our file that we gave to players. The input was 2. This had to have been 14 in order for it to trigger the 16 block size, and then have a full block of padding on the end. So we know that this guy is 14 bytes, okay? My flag format, or the flag format of the CTF, ends up being something like this, right? So what we're going to really try to do, and this doesn't have to be the input. This is 16 characters. Maybe this one doesn't conform to the flag standard, or maybe it's not looking for flag. Maybe if I'm able to give it the correct input, it then reads a file or something. But this is the exact challenge. So we can kind of guess what our first few characters are going to be. And then even if we don't guess what they are, we're still going to be able to find it out. So we know that it's either like this, or maybe it ends up being something like this. Might be our best guess. We just don't know. There's that many characters that we're looking to solve here. So how do we do this? Okay. So I'm going to show you the kind of trick or the guess here of how we do this. I'm going to use some characters and encode them a certain way. So A is our input. So if I type in some characters, that's what it's going to be. The flag characters are going to be F, capital F. Our padding is going to be a question mark, and our guess byte is going to be a G. So let's say I enter just one A. What it's going to end up doing is add 14 bytes to that. That A plus the 14 is only 15, and it's going to add 1 byte of padding. If, however, I then reconnect and add 2 bytes of something, it's going to slap on that 14 bytes, and it's going to have to pad an entire block size, which is going to be another 16 bytes on it. So let's say I go ahead and add an exact block size, which is 16 bytes. It's going to have to slap on its flag, which is 14 bytes, plus another 2. Here's where things get really interesting. Instead of adding 16 bytes, what if I only add 15? What's going to happen is we get 15 bytes. The part from the flag we're actually going to have in our first block is going to be 15 bytes of characters that we know, plus the first character from the flag. Then after that, it's going to be the rest of the 13 characters from the flag, followed by 3 separate padding bytes. We're going to record this, right? Because what we're doing is we're essentially leaking that first character of the flag. Then what we're going to do is we're going to come back in, and we're going to add 14 characters now, and then, 15 characters. But what we're going to do is we're going to add a guess in. So if we can guess that first character, the actual block that comes back to us is going to be the exact same, that first block. Second block is always going to be different because there's different padding bytes and things going on back there. But for the first 32 characters that we get back, or the first 16 bytes, if that matches our reference block, which is right here, we know that we found an actual match. So what we do is we force the algorithm on the backside to actually put our first block with the first character in the flag, and then we start sending data to it and try to enumerate all the different characters. So for this guess character, I'll do a lowercase a, b, c, d, e, f, g, all the way up to z. Then I'll do uppercase characters. Then I'll do numbers, and then I'll do some special characters. I just happen to know that these are what's in here, so you may want to add other special characters, of course, to start going through this process if you're not finding things. So let's do this by hand, and then I'll show you how my script solves it to kind of automate this process, because this is a little rough to do by hand. All right, so I'm going to connect, and I'm going to give it a full 15 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, now I'm going to record this, because what happened was in this very first block, what it ended up encrypting is going to be 15 A's plus the first character of our flag. So now when I connect again, I'm going to give it 15 characters, but I'm going to guess what my next character is. All right. So we're going to continue to do this process over and over and over again until I guess the right character. And when I guess the right character, the beginning of this is going to end up being the same thing as my reference. Holy crap, that is awesome. Inevitably, what we end up doing is sending fewer and fewer A's that we control, pushing the known values of the flag over and over and over until we finally get the full flag. All right. So the way that we automate this is a little weird. I'm going to be using Telnet lib. I give it the host and port information. I have some receive prompt and stuff here. I'll go ahead and just leave this up so you can pause it and see what I have. Then I'll go ahead and scroll down and you can see this information. If somebody reminds me, I'll post this on GitHub so you can have and play with everything if you need to or want to. Okay, So I know that my flag's length is 14, so I'm just going to continue looping over this process until my flag length is actually 14 or greater. I'm going to connect to Telnet. I'm going to get the reference block. The reference block is going to be 15 A's followed by the length of my flag, which is in this case going to be 0. So it's going to put 15, and then it's going to force, remember the actual challenge for this ends up stripping off new lines and stuff. So I do add, I'm actually sending 16 characters on the first one, but this new line is required to send data over Telnet. So that ends up getting stripped off anyway. So what we end up doing is collecting this reference block. And what we're going to do is we are going to, at some point in get reference block, it only takes the first 32 characters. What it's doing is this no value populated in here means start from the very beginning. I can also do this, but it just means start at the beginning and go all the way up to the 32 index and take that. This means we're only taking the first block. It's 32 bytes because it's represented in ASCII hex when it comes to us. If you convert that to actual bytes, it's 16. So I hope that makes sense. That can be a little confusing. So we're still working with 16 byte block sizes. Then what I'm going to do is I'm going to connect again over Telnet, and I'm going to receive the prompt, which basically just says, give me the junk that it asked me to. Then I'm going to send 15 bytes minus my current flag length, which is 0, plus the flag, which again is nothing for the first round. And then I'm going to send the first char and char set. So it's going to send an A. So I'm sending 15 uppercase A's, and then I'm going to send a lowercase a. And then we're going to get that back in received. Received is going to decode it. It's going to reference the ciphertext portion of that JSON block. So it's going to give me this back. And then what I'm going to do is I'm going to take only the first 32 and I'm going to compare it to my reference block. And if it's there, I'm going to match it, add the character onto my flag, and continue this process over and over and over again until we finally get the result. So let's see this bad boy in action. It's actually kind of cool to watch. All right, so now it's going and sending over its stuff. As soon as we get to capital H, it should trigger. There it goes. And now it's sending 14 A's plus my first character that I know is correct. And then it's enumerating the second character. Once it hits a T, it should switch, match. All right. Now it's sending 13 A's plus an H plus a T. And then it's enumerating that next character over and over again. Should get to an H. Then it switched again. Now it's sending 12, 13, 14, 15. Yes, 12 A's, HTH. And now it's going until it tries to find that open curly brace. And once it does, it'll be here soon, it triggers and goes to the next one. I'm probably going to speed this up in the video because it's interesting and cool to see, but I'm not going to make you watch all of this. Okay, wow. So that took a little while to solve. I should have timed this to see how long it ends up taking, but it's not too bad. So you might be looking at this thinking, wait a minute, is this fuzzing the actual challenge? And am I doing something wrong here by like violating the rules of the CTF? And we're not at all. The reason why is because this is just something that we know has to be done to solve this type of challenge. So hitting it over and over again with systematic input that makes sense, that's clear and understandable, that we can observe and say, this person's on the right track to it. They're not just abusing it. If you just load up Python and just do like OS rand or something and just get random bytes and then start throwing them at the service and do that for 12 hours straight, it's not going to work. We're going to end up trying to ban the IP or just make sure that it's not affecting the service and other players. But when you're doing something like this, this is totally fine on most CTFs. This is not just a blind fuzz or a denial of service attack. It's a systematic approach to solving a problem. So this is totally cool. And what we'll do is copy this flag leak, which is the actual flag, and we'll go back over here, type this guy in and submit it. The question you might be asking is, that's not fair, or the thing you might be saying is, that's not fair. How am I supposed to know that works? How am I supposed to know that this article is out there? It really comes into the thing that there's some information, there's some intuition. I know that there's a way to get the flag, and all I really know is the information from the actual encryption service. And when I connect to it, it's telling me that's AES ECB. Sometimes what I'll do is I'll just say AES ECB crypto CTF challenge solve. and start looking through past CTF problems and asking myself, like, what did they use? What was that problem like? Does it look similar to this problem? Things like that, right? This problem is really, really awesome. And actually, it's sort of taken from CryptoHack. If you like this kind of stuff or you want to learn about this stuff, CryptoHack is like legit. It's sort of like CryptoPals, which was sort of an older version of this, and CryptoPals is still really awesome too. CryptoPals walks you through a lot of different things like XOR, single byte XOR. It starts going into AES. There's lots of different things. It goes over hashes, Diffie-Hellman, all these types of cryptographic primitives. CryptoHack is a really nice thing that sort of gives you points. This one, I think you had to like email in your values or something. It's been a long time since I've done CryptoPals, but CryptoHack is super, super nice. You can register for free, log in, and start kind of going through the scoreboard. Once you solve a challenge, you can look at other people's approaches to solve the problem, and it sort of eases you into everything. And it starts kind of giving you introductions, how to format the flags, how to work with the challenges, and everything is kind of built out to a nice REST API. So you can actually just use something like Python requests to send data over and get information back. Or you can do it right in the browser. They have like a way to interact with the challenges over the browser. Super, super nice. I ended up solving one of that challenge on this one, end up re-implementing it for the CTF in Python here for just like the normal interaction of it over SSH or Netcat. And it ended up working really, really nice. So, thanks to CryptoHack for inspiration on a lot of these challenges. And yeah, that's pretty much it. So hopefully this made sense and hopefully you learned something about this. Give it a shot if you want to. Otherwise, thanks for watching.